Yes, very well.
Okay.
Good. Hello, everybody. I'm Jinhua Zhao, Professor of City and Transportation Planning at MIT. Welcome to the MIT Mobility Forum, organized by the MIT Mobility Initiative. Today is really my great pleasure to have Professor Daniela Rus and Dr. Alex Amini join us to talk about their recent effort in building the Vista and talk about the data-driven simulation for resilient and sustainable mobility. Before I formally introduce the speaker, just to warm up the audience here, I prepared a brief poll, which asks you your degree of interest in autonomous vehicle or automation in general. Yeah, is this your primary research or professional interest, your secondary research interest, or just curious? Yeah, to see how the audience in this. All right, we got 100 participants responses now. I'll give 5 more seconds. All right, so I'm sharing the result here. Daniela, Alex, can you see it? Primary research interest, 21%. Secondary interest, 40. Another 40, just curious, right? Okay, thanks, everyone. Secondly, I will invite everybody in the chat to type your organization and the local city so that Daniela and Alex know a little bit about the audience here. So I would say MIT, Cambridge, MA, University of Calgary, Lincoln Lab, Aerostro, Green University, IT. Okay. Okay, next, sir. Thank you. Yeah, please keep adding that to the chat there. Lastly, I want to mention the norm of this forum is everybody contribute one idea, right? This is to the audience here. If you're here, choose to spend 1 hour, please contribute either a question or a comment. I type it into the chat, right? And this turns out to be a very valuable resources that we'll compile and share back with the speaker. Speaker often appreciate this. So thank you again in advance for everybody to contribute in this. All right, so let me introduce Daniela Rus is the Andrew and Ernie Vertelby Professor of Electric Engineer and Computer Science. He is the Director of Computer Science and Artificial Intelligence Laboratory, CCL at MIT. He's also the Deputy Dean of the Research in the Schwarzman College of Computing. Her research are in the robotics and artificial intelligence, and the primary focus is to develop the science and engineering of automation. And Russ is a class of 2002 MacArthur Fellow, a fellow of the ACM, AAAI, IEEE, and a member of National Academy of Engineering and American Academy of Arts and Science. Dr. Alex Amini is a postdoc associate at CCL with Professor Rus. And he's also the co-founder and chief scientific officer of Semis AI Incorporated. And his vision is for a world with adaptive, autonomous agents capable of learning to interact in complex, uncertain, and extreme scenarios, supporting people with cognitive and physical tasks. Its research includes learning end-to-end control, i.e. perception to actuation autonomous system, formulating confidence of neural network, and the mathematical models of human mobility. So without further ado, let me give the forum to Daniela, please.
Hello, everyone, and thank you for joining us to talk about autonomy and how to use data to make autonomy more capable and safer. Now, for a number of years now, Alexander and I have been working together towards this great aspiration to build a car that will never be responsible for a collision and become your friend. And at the beginning of our efforts, we took a very kind of traditional model-based approach to solving this problem. We thought about what is needed, what skills a car needs in order to navigate in the world. A car needs to map the world. It needs to be able to localize itself in the world. It needs to find the obstacles in the world. It needs to know how to go from here to there. And all of this is really exciting, and these topics are the subject of many research programs. With Alexander, we started thinking about the role of data in enabling cars to be much more agile, to drive much more like humans. And in the process of doing that, we have found that, in fact, before you can actually use data, you need data sources. And these data sources had to include examples that covered the space of all possibilities for driving in as exhaustive a way as possible. Now, in driving, we want to think about what happens in near accident and accident situations. And these are not easy cases to get physical data for. And so Alexander had the idea of building a simulation system called Vista that allows us to use real-world data examples, and then in simulation turn those examples into anything we want, so that we can train our vehicles to deal with very difficult driving situations, not just with safe, boring situations. Vista was recently open sourced, and this is really important because up until now, I would say that the researchers who have access to the kind of data and simulation capabilities that Alexander's system Vista has are companies, and all those simulators are proprietary. With Alexander's work, the simulation, the ability to simulate in a broad way to describe complex and difficult scenarios that truly get a vehicle to learn something new. Up until now, this was only available if you worked at companies. Now, this work is available for all. And Alexander will tell you exactly how we got there. Alexander, please take it away.
Thanks, everyone. And thanks, Daniela, for that introduction. Thank you, Professor Zhao, also for the kind introduction. And good afternoon, everyone. I'm absolutely thrilled to be with all of you today to really share this research vision that Daniela was just telling you about. And I think that vision for us, at least, is deeply rooted in autonomy. Actually, we believe that integrating autonomy into our society, whether that be at the vehicle level or even at the city level, could absolutely revolutionize urban mobility towards being more safe, efficient, and sustainable. Now, this vision of mobility really rests on this ability for these autonomous solutions to be seamlessly embedded and woven into this incredibly complex urban fabric that we have today. And I think achieving this vision really requires new technological solutions to understand and adapt our rapidly changing transportation systems that we see, and that these systems really are seeing new and unexpected and very harsh uncertainties every single day. We believe a key part of this solution, like Daniela said, lies in the problem of data. And since if we had basically a way of collecting data from these very harsh or rich conditions, then there should be a path forward to realize this dream by learning from these pieces of data. But by far, the most successful way of realizing this level of resilience through data has been actually by placing autonomous systems actually into the physical world and allowing them to interact and learn from their environment. Now, this is not only slow because it's limited to real-time executions, but also it's expensive and oftentimes prohibitively dangerous, especially for these very rare edge cases that we care about the most. Now, on the other hand, simulation presents an incredible opportunity to training and governance of autonomous systems, where we can actually define these challenging edge cases and stress test our system offline. But unlike the real world, even the best simulators today still produce this huge gap to reality, making direct transfer, what's called sim to real transfer, still a huge barrier. This is actually because the vast majority of simulators today are what are called model-based. This basically means that they're built from models of the world. These models are oftentimes curated by human artists or designers and can include both the physical appearance of that world as well as the physics and the dynamics and the behaviors of everything that moves in that world as well. Now, these simulators are very modular, but they lack the ability to capture reality. And even after decades of engineering these types of engines, they still face this infamous sim-to-real gap. Now, on the other hand, data-driven simulators are fundamentally different in that they are built and rendered directly from raw data of the real world. So in contrast to the very well-studied sim-to-real problem, these simulators are what we call real-to-sim, and they pave a path forward towards a more resilient and sustainable autonomy future by leveraging massive data sets that already exist to scalably build these new synthetic worlds. So specifically in today's talk, we will share our work on building what we call the Vista simulator as a step towards achieving a more sustainable and resilient mobility and transportation system. Now, Vista is very unique, like Daniela said, because it is fully data-driven, and it can harness the power of these massive data sets that we have available to us in order to synthesize very high fidelity, very photorealistic, harsh edge cases, which are too expensive or too rare to go out and collect in reality. Now, the work that we'll be presenting today is actually the culmination of many years of research to establish a principled approach towards data-driven simulation. And only a few months ago, we decided to open source Vista, becoming the first data-driven engine for mobility. And since its release, it has amassed over 7,000 independent installations, with about nearly 100 new installations of the simulator every single week. So Vista is, like I mentioned, data-driven from the ground up. And that really combines real data with concrete physical properties of different sensing mechanisms. And that's in order to achieve this high fidelity and extremely photorealistic simulation across these different modalities. Now, we extend this philosophy of data-driven from the low-level sensor physics to the environmental level, allowing us to rapidly scale simulations across tens of thousands of kilometers in a variety of different types of weather, lighting, and geographic conditions. And finally, we will show and discuss how we can build these types of data-driven engines for higher level behaviors as well, to capture rich human-like interactions of multi-agent systems and combine this with our perception suites, like you see on the first two panels here, in order to achieve this very comprehensive data-driven engine or suite across these different levels of mobility. So in today's talk, we will discuss recent work on advancing each of these levels within Vista and basically use these icons at the bottom to contextualize which stage we are in this process of the simulation. So first, I'll just start with an introduction to what Vista looks like, and maybe I'll start with the simplest possible example from Vista. So at its core, Vista leverages real-world data instead of pre-modeled scenes to enable learning control policies end-to-end, entirely within the simulation engine for direct deployment into the real world. We can start with the raw data collected by a human driver on the highway on the left, and from a video camera mounted on the car, using our simulation engine, Vista, we're actually able to synthesize this brand new trajectory. For example, here on the right, a trajectory of a vehicle oscillating on the same road, but now it's of this virtual agent, not of the raw data collected on the left-hand side. So how does this work basically step by step? How can we achieve this kind of photorealistic simulation directly from raw data? Well, the core is indeed the data itself. So let's kind of step through this, starting first with a single image that comes from a camera collected by that vehicle. Now, each pixel in this image is denoted by an RGB color, 3 numbers. And for every pixel, we can also use data-driven methods, neural networks, and artificial intelligence to estimate the depth for each point in this image. So it tells us not only the color, but also how far away that pixel is from our object or from our agent. Now, we can, with that combined information, we can project every pixel in our image out into 3D Cartesian space. And in fact, from extrinsic calibration of the camera, we even know exactly where the original vehicle was in this projection, the vehicle that collected this image. We can visualize that vehicle and the scene itself from many different new viewpoints or vistas, hence the name. And once we have this environment, this three-dimensional environment within Vista, we can now spawn new virtual agents into the scene and synthesize their views as they move through the scene as well, and brand new viewpoints, translations, rotations, and so on that may have been too challenging of edge cases that we couldn't have collected in reality. We can perform this projection of information from 3D back into the 2D camera by mimicking the physical ray tracing process of light as it bounces off an object and gets collected by the camera sensor. But different sensing modalities have extremely varying physical properties that are built into Vista to enable this rich multimodal simulation. So for example, unlike cameras, which passively collect the light photons from the environment, LiDAR sensors, like you can see in the middle, actively emit rays and measure the time until return in order to estimate geometric distance and geometry of their scenes. Or event-based cameras on the right-hand side, which are really dynamic vision sensors and measure asynchronous streams of light differentials. And with this very flexible multi-sensor simulation suite in hand, we can drop many virtual agents into our environments. And in the beginning, these agents don't know anything about the rules of driving, or all they're doing is they're dropped in this environment and they get to interact within the environment, within Vista, and observe all of this simulated data and see how they can learn to drive, or really to not crash and successfully navigate this new environment that they're placed in. This actually enabled the first fully end-to-end policy trained entirely using reinforcement learning within simulation and directly deployed on board a full-scale autonomous vehicle in the real world, which you can see here on the left-hand side. Now, these policies, again, just to reiterate, were trained without any human supervision. They were only interacting with the very sparse reward signals in simulation and were deployed without any adjustments or transfer learning. And we benchmarked these types of decision-making systems and policies against other state-of-the-art sim-to-real methods, and even compare our training to training on the full extreme, the opposite extreme of the spectrum, which is training only on real-world data, right? So no simulation at all. And not only were the agents that were trained within Vista capable of this direct transfer into reality, but even more impressive to me was that they were vastly more resilient to unexpected edge cases than their counterparts. And they were actually more robust than even the models that were trained using only real-world data. So these models that were trained within the Vista simulator, because they were exposed to all of these edge cases in simulation, actually turned out to be far more robust than the models that were trained on entirely real-world data because of that limited viewpoint and the inability to capture all of that richness from the scenarios and situations. Right, so this is, I think, points to the fact that Vista enables not only leveraging the very clean or standard real-world data that we collect, but also to photorealistically synthesize those risky scenarios like nearly crashing or going off of the road. And furthermore, because these environments in Vista are digital twins of reality, we can scale our training and evaluation of autonomous systems seamlessly to tens of thousands of kilometers. And this scale of photorealistic simulation would typically require a cluster of mini computers with today's model-based simulation techniques. But here in this slide, we're actually showing videos of trained virtual agents in simulation driving through many thousands of kilometers on a single desktop computer for a matter of hours and learning to complete this task to be deployed into reality. This scale of simulation extends beyond the magnitude of the kilometers, right? Vista provides an algorithmic approach to actually training a variety of different environments, ranging from daytimes to weather conditions to geographies and also road structures as well. And this all stems from this data backbone of Vista. And in fact, it's even possible to multiplex our data sets together to achieve even greater scale of these environments. So for example, by observing a lot of data from both winter and summer, it is possible to build models that can re-simulate what this winter scene you can see here would look like in the summer. Or if you look at them side by side, before and after, you can actually see how these data-driven techniques can pick up on key salient features in their domains. For example, adding leaves to branches in the summertime or dirt on the road where there used to be snow, or my personal favorite, which is actually adding shadows that were not there during the winter, but need to be there because of these new leaves that exist on the trees and the sun that's coming through them. And while I think that this is extraordinarily exciting, it's still left us wanting more, because so far we've only talked about simulating perturbations to our physical vehicle and the sensory systems, as well as the environment that they live in. But real-world mobility and transportation systems are far more dynamic and have agents around us as well, operating in the scene, impacting our decisions, our policies, and our traffic flows. While many traffic simulators do exist today, in Vista, again, we're trying to aim to take a radically different approach by leveraging real data of human behavior to build superior human-like simulation of interaction. And ultimately, the goal here is to combine this behavioral simulation with Vista's perception simulation to achieve training of multi-agent decision-making. Now, we saw earlier that this underlying Vista worlds already live in the three-dimensional space and are basically projected back into the desired sensing modality. So this means that we have a way of basically seamlessly adding new 3D data scans of, let's say, a new vehicle that we want to inject into this Vista scene. And we can have it rendered in a geometrically consistent manner with the rest of the scene. But simply placing this vehicle into the scene is only one half of the story, since we still need a way of simulating its motion and making sure that its motion is also congruent with realistic and realistic driving behaviors and traffic patterns of reality. So to accomplish this, we are building data-driven models that can leverage large data sets of real human mobility interactions. Starting with these data sets, we can actually label the locations of trajectories of each mobile agent. And these agents can then be tracked through time to build a data set of mobility that we can actually learn from. Now, through this process, we can learn to not only predict the trajectories for these agents that were already in our data set, but we can spawn new agents and we can generate new trajectories that are congruent with the original human behaviors. And we can sample these many times and under many different types of scenarios and situations to realize this diverse edge cases of interactions and traffic patterns, giving us a huge scalability boost in the power of these simulation techniques, but while still maintaining the huge power of data-driven realism that comes from using real data. So these data-driven trajectory models enable the simulation of basically where and how agents should move. And we can combine this with our perception and sensing suites to understand not only how they should move, but how we can actually build this into a comprehensive platform for multi-agent simulation, ranging from simple tasks like on the left-hand side, like a car following task, to more complex dynamic behaviors and dynamic tasks like dynamic overtaking on the right-hand side. Now, again, the policies trained within Vista are capable of transferring directly on board our full-scale autonomous vehicle without modification. So here again, we're showing an example of this, where we can show how these policies generalize to the task of dynamic overtaking. In this form, actually overtaking another autonomous vehicle, which is hugely different than any vehicle that has actually seen in its training data set. So not only is the task itself transferring to reality, but we're showing also transferability and generalizability to other types of vehicles. And again, this is largely due to the fact that in Vista, we're exposing these agents to such a wide scale of different data, enabled through the data that was used to generate the platform of Vista, coupled with the actual platform itself to augment that data and scale it up even further. Now, putting this all together, the Vista simulator provides a very flexible, modular, and highly scalable engine for mobility simulation, starting from the data-driven environments and the scenes that they live in, to the agents that can be added to those scenes. Now, with a variety, those agents can come with, like we saw, a variety of different physical and multimodal sensing mechanisms in order to simulate, train, and evaluate policies for very sustainable and resilient mobility. we're especially excited about this entire line of research around Vista. And we already got a sense in this talk, or I tried to share a little bit about how these data-driven simulation methods allow for greater realism and scale, but we can actually go far past this as well. And specifically, one key benefit of these types of data-driven simulators is their ability to achieve very resilient mobility, because you have to be able to adapt to uncertainty and unexpected events that may occur. As part of our research, we've actually created a lot of new types of data-driven methods that can be integrated together with data-driven simulators like Vista in order to propagate uncertainty throughout the entire simulation pipeline. Now, this can be critically important, not only for the decision-making task, to make our decisions aware of our uncertainties, to make more uncertainty aware and structured decisions, but also for the purposes of governance and policies. Having this level of uncertainty estimation is critical if you're going to be relying on these types of simulation and modeling-based techniques for developing new policies that can impact the mobility systems of the city. And finally, one of the most exciting future opportunities of this space is that, unlike model-based simulation, data-driven simulations or simulators like we've created in Vista are so fresh and so new and expose so many exciting opportunities and challenges for mobility and beyond. And with Vista, we're trying to present a very principled approach to building these closed-loop feedback engines directly from data. Now, what we discussed today is the context of when the vehicle itself is the decision maker. It's the action taker. It senses from its environment and it takes actions. But these techniques, these data-driven techniques for data-driven simulation can actually enable high-fidelity simulation at the city or governance levels as well, where actions are not only taken by the agents, but also actions can be taken by the environment and the policies that we enact in those environments to tackle some of the world's most pressing and inspiring mobility and environmental challenges. With that, I'll conclude and thank my many collaborators, many of them who are here today, who have contributed to this work, and again share that we have open sourced a lot of Vista. Not all of what I presented today is open source, but we're continually building out these features and adding them to the open source release of Vista. You can see some instructions, or you can visit the website on the top right for documentation or instructions on how to install and become part of this community. Thank you very much.
Great, thank you, Alex, and thank you, Daniela. This is really brilliant, and also really grateful that you actually open sourced this whole effort to the entire community. That's a major contribution. Thank you. So I'll start with a little bit technical question, and gradually move into what it means for the, say, competition with the company, the commercialization, the whole society, etc. Right. So now from the more technical one, you mentioned there are 3 levels of data-driven engine, from the physical, then to the environmental, then to the behavior, right? Can you share do they require really different type of methodology to tackle each of them, or they actually share a fundamental similar principle that you capture?
Yeah, I'm happy to take this first. So I think the backbone of all of these, it's quite interesting, because actually a lot of the backbones for data-driven simulation has not really been developed yet, because these techniques are so new. So a lot of what we're trying to do is actually establish, that principled backbone of how we can unify a lot of these themes to avoid kind of very scattered research across these different domains. The way we've targeted this so far has been unifying it in the representation space of the data. So taking your data, whether that be camera data, but it could also be other types of multimodal data modalities, and trying to unify that into a common space so that all of these sensor modalities can be shared, so that when you want to simulate, let's say, a new sensor modality, you can leverage from this common space. That gives you a very unified way of dealing with the physical simulation and also with the environmental simulation, because both of those live in that physical space. The behavioral simulation, though, is quite different, right? Because it's not only about the environment, but also about the agents that interact in the environment. Now, oftentimes what we found is that those agents rely not only on other agents, the motion of other agents, but the environment itself. So it is important to also rely on that shared physical space. And we're still finding ways to incorporate the behavioral models with other agents, but that's still a very open question and a very exciting line of research still.
Yeah,
so I would just like to add that it's in fact the picture that Alexander has on the slide here is very relevant, because we really have a hierarchy of simulation capabilities, and you can think of it as a pyramid or a cylinder, however you want to imagine the hierarchy. But the higher up you go in the hierarchy, the higher the level of abstraction in some sense, but the abstractions build on the representations that Alexander has talked about. And so we have common representations that enable us to put different sensors underneath them. From these representations, we can also make connections with the environment, and then we can put higher level behaviors and abstractions on top of that.
Thanks. The second question is about the edge case construction here, right? Everybody talking about this is a key challenge. They are critical of safety, but it's highly inefficient to learn if you just use real world data, right? The way you're doing this is you absorb this real world data, distribute the structure, and then you inject variations, create these new edge cases, right? So tell us a bit more the strategy of this construction new edge cases, and how do you make sure that the ones that you constructed are relevant to the reality, or there will still be surprise that you wouldn't know how to construct such very extreme edge cases, for example.
Yeah, so actually this is an extraordinarily interesting question. I think there's a lot of opportunities here. So I can share maybe two ways that we've tackled this problem so far. The first way is a very traditional reinforcement learning mentality, where basically you say that the construction of these edge cases is not for humans to decide. It's actually something that should be decided through interacting with the environments. And if you don't observe these types of edge cases, then perhaps they're not of enough utility for the system. So the mentality in this case is, let's unleash our virtual agents into these types of data-driven environments, and let's allow them to interact and find all these edge cases. If they don't observe them, and through a much larger scale, a more sustainable scale of data collection, we can actually do this in virtual simulation compared to real-world settings, then that gives us already a great foundation of dealing with edge cases, because in this interaction with the environment, we can already be exposed to a lot of these cases. Now, the other regime is something that we've started more recently, which is taking a much more principled approach towards targeted edge case curation. And in this case, we're actually trying to optimize, almost solving an optimization process between two objectives. One objective is trying to increase the uncertainty or the ambiguity or the stress of the mobility system that we're trying to curate. And we try to create edge cases that will propagate the maximal amount of uncertainty for those systems. Now, on the other end, we're trying to, it's a dual optimization process, because not only do we want to maximize the uncertainty of those edge cases, we also want to minimize kind of the deviation and the real, or capture the realism still of the environments. Because of course we can create many types of very challenging edge cases, but they're almost impractical for real world use, and it's almost not fair to the system. So a lot of what we're doing now, especially towards the end of the talk, I was hinting at this, with this uncertainty propagation of the systems, is to not only propagate the uncertainty through the simulation platforms, but also propagate it through the decision making to achieve uncertainty-aware decisions, so that we can actually tackle these types of questions and solve these types of very challenging edge cases that are still realistic.
So I would just like to add that in fact this is where we are with reasoning about edge cases. But at the beginning, when we started this work, we were very interested in accidents and near accident situations. So we were interested in simpler things but things that occur a lot. For instance, I was rear-ended on the mass bike yesterday, and this was while I was changing lanes. So that's this, and this is not an uncommon event. So we actually did start with some common types of situations that we wanted to avoid. But then we had people asking us, well, so suppose a plane is to do an emergency landing on the highway. how would you respond to it? Can your system adapt to this? And like, if you think about this, the idea of a plane landing on the highway is something that happens very rarely. But when it happens, I guess we as humans understand the semantics of the emergency landing, understand what a plane is, and we kind of understand what the response to a situation like this might be. And so we started thinking about how would we connect real-time performance with unexpected events that the system wouldn't have seen before through reasoning and decision-making. And so there is a lot to be done here, but and primarily because our robot cars don't have the same range of knowledge and insight that humans have. But at the same time, we're not deploying these systems yet. So, or we're deploying them in very limited scenarios where we don't really expect the plane to be landing on the highway.
Great, thanks, Daniela. The last set of questions from me, and then we'll give it to Bhuvan for the audience question. Let me encourage everyone to add your questions, comments again to the chat as well. So the last one at the beginning, Daniela mentioned there's a strong asymmetry between the large corporations' access to data versus academics, and also even like small companies, for example, right? So thinking how I have a feeling that your work can potentially really change that situation, right? At least contribute to a rebalancing between the two. And then from the large corporation point of view, their advantage of having the large data set will relatively diminish in that way, right? So for that, I'd like to see your view about how the whole play between academia and large corporation play out in this.
Alexander,
I think so. Actually, this is one of the things that really inspired us and made us pursue this decision, because we do think that this is really a fundamental technology and really a pivotal reframing of how simulation is done. Even in these industry companies, very large-scale industry self-driving leaders are taking a radically different approach to simulation. And you can see, especially bigger companies like Google and Waymo, decades of research into self-driving, but invested into the model-based simulation. And they're continually trying to build up the realism of these model-based simulation engines. And within a few years, actually, by leveraging and properly restructuring the problem formulation, we can leverage the real data and build much more realistic engines from this data. So we're really inspired by this reframing of the problem and how that will, reshape the way that these communities think about how it's possible to capture the very harsh uncertainties and edge cases of these real world systems, not only in mobility, but I think there's huge potential for data-driven simulation far beyond these types of systems as well. And by open sourcing it, we actually wanted to, like you said, even the playing ground between these two fields. We've already started to see a shift in industries now moving away from model-based simulation engines, now closer towards data-driven simulators, because they actually do have these large data sets. They have the tools and the mechanisms to build very high fidelity engines like Vista within their own organizations. But I think even taking a step back from, let's say, industry versus academia, I think this presents another very exciting possibility, which is for the governance of autonomy as well. Because I think right now what we're missing is a unified framework for evaluating policies that are deployed onto real world cities and streets. What I'm excited about with this work is actually it can start to serve as the framework, a unified framework that's very high fidelity, very photorealistic, both in terms of what we see, the physical environments, as well as the behaviors that exist on the roads, to establish this baseline for governance and how we can have mobility systems, autonomous mobility systems that can be seamlessly integrated into society with our existing transportation networks and so on.
Daniela?
So I will just add a few thoughts to this, and I will observe that for many businesses, the businesses with the best data are the businesses that have the most success with machine learning. And machine learning is very powerful today. Now, with these open source tools, what we're doing is essentially we're we're leveling the playing field. Because we're saying we have this way that makes it really easy for people to have data in the space. Although Alexander said that the work is extensible to other domains, but we're leveling the playing field. We're making it really easy for data to be generated, and this is good quality data. We also have a suite of algorithms that allow us to test the quality of the data, to figure out, given a space, where do we have data, where do we have too much data, where are we missing data. And so with tools like this, we can sort of bring everyone to the same onto the same level from the point of view of data. And that means that we open the possibility of innovation and of making progress in many more directions. We open to other university researchers who may not have autonomous vehicles to collect data or special sensors to collect data, but they could build on top of the Vista engine, and they could put new capabilities. We also open to small businesses who may not have machine learning expertise in mind. Although I would say that Vista is open sourced and freely available for research purposes, not for commercial purposes.
Thanks, Daniela. Thanks, Alex. Now I give to Bhuvan for the audience question.
Thank you so much. This has been fascinating. We have like a bunch of questions. I'll try to like theme them in various headings so that we can get through them. So the first question I think is about data, like with any AI system. Spencer, Johan have, touched on this point that have you all formed any methodology to validate the data? So you all, you mentioned it's a digital twin, Vista, the digital twin. So with any AI system, you do some sort of data augmentation, to get the AI to learn it better. So is your simulation limited by the quality of data? Do you all have any methodology to, validate this against the real world data, once the system is done processing it? And you mentioned, combining the behavior with Vista simulation to get the best of both worlds. So just a bit on this whole, how do you collect the data, ensure, this is the best form of data that you all are getting, and then ensure that the output is also, on par with something you would not get, rear-ended on the Mars bike again.
Yeah, I think this is a excellent question. So the fundamental approach that we're taking to this is a very technological approach. So we definitely agree with this assessment that not all data is equal. And especially when simulating and generating new data, it's especially important to keep that in our minds so that we're not actually polluting whatever we're training or evaluating based on incorrect or faulty data. And the approach that we're taking for this is actually one that's especially suited for data-driven simulators. And that's the ability to have data-driven uncertainty estimation techniques that can be built into the AI systems that are actually generating the data and processing that data so that we can actually propagate that uncertainty all the way from the data space through to the predictive models that are actually generating the data, and even all the way to the other end in the rendering and the actual simulation of that output data feed. And we can actually sense the data at all sense the uncertainty, propagate that uncertainty throughout all stages of this. And this gives us a very quantitative understanding, both in terms of quality of the data, how noisy that data is, for example, not only the data from the sensors, but also the labels as well. Both sides of that are critically important, as well as, like Daniela was saying, the imbalance of your data. So we've built a suite of computational and quantitative methodologies for data-driven neural networks that can not only understand and propagate the uncertainties, but also propagate these imbalances in the data distributions as well.
I mean, that's an excellent answer. I would just like to emphasize that the reason Vista works so well is because we do start with high quality data, but high quality means really high resolution, high fidelity. Once we have a car trace that has high fidelity and high resolution, then it's easy to do all the processing that Alexander described. If the data from the sensors is fuzzy and low resolution, then it's much harder to reconstruct the 3D scene as you have seen.
I think the last question on data. So a couple of people, Sanjay and I think Ignacio have this question that, are you going to make some sort of an interface for public data sets? So, people can use Vista, plug in their own data sets into it, some sort of crowdsourcing for the input data that would really, increase the number of, data points, make VMTs, that you can process. And I think Zuan had a question on, have you all considered other, sort of actors such as bikes, pedestrians, scooters, motorcycles, because we didn't see some of those in your images so far, to take as inputs.
Yeah, definitely. So maybe on the first question first. So yes, definitely. This is something that we're doing right now. We actually already have preliminary results where basically the input to Vista can be not only our data that's collected, but you can think of it almost as a conversion function that can take an arbitrary data set that's coming from, let's say, Google has open source their self-driving data sets. Can we have a conversion function that converts a Google data set into a Vista compatible data set? We've already shown this for several data sets that are open source, very widely used in the community. We're going to basically create a structured or principled approach to doing this so the community can not only achieve, training on not our data sets, but more importantly, that they can evaluate the algorithms that they built on these other data sets within a closed loop feedback system of Vista. I apologize, I missed the second part of the question.
It's about the actors. So the images,
Yes.
didn't have like pedestrians, bikes, scooters,
Right.
So just wondering if that's also, on the table to include, make it more complicated.
Yeah, for sure. Definitely more complicated. We haven't done this yet, but extremely interesting to do. Like I mentioned, the field of data-driven simulation is one that we've really started only a few years ago. In comparison to model-based simulation, it's extremely new. And a lot of these, there's so many exciting areas and opportunities for future improvement. This is definitely one of them. The complexity of the agents, also incorporating more complex multi-agent behaviors with those other types of agents, right? A car will behave very differently next to another car versus next to a bicyclist, right? And how can you capture that into your behavioral models as well, not only the physical simulation of those agents?
Thank you. I think we'd probably move to hold on. Yeah, so I think a couple of people had questions, on hardware requirements for processing all the data, if they could implement this on their end, and generally, on the whole commercialization aspect of it as well. So do you all, it's currently open source, but in the future, what is the long-term plan for this? So if you could quickly, just say a couple of sentences. Thank you.
Yes, of course. Sorry, the first part before the commercialization, could you repeat that part?
If people would want to implement this at their end, hardware requirements for,
yes.
This sort of a simulation, is this something which only big companies can do, or, a
Right.
couple of NPDIs in, in an array and you can do it at home?
Yes. Yeah. So actually, this was something that we wanted to prioritize very heavily when we were building the simulator. So we did not like this trend of, if you want to train in simulation or test in simulation, you need these large supercomputers. We were not happy with that trend and the way
Or
the
pay
community
Google
is
a lot
going.
of money.
Exactly. Yeah. So we actually wanted to build a data-driven simulator that was locally simulation, right? So that means that you could have a very large data set, tens of thousands of kilometers, but your simulation of the agent is only happening just locally around you, right? Just based on what you can see around you. And that was actually capable, that just formulation alone was capable of basically transforming this scale of simulation that we could enable through methods like Vista. So I mentioned a stat earlier, which was that we could actually simulate and train our vehicles on tens of thousands of kilometers of road within a matter of a few hours, right? And then those policies would then be deployable onto real cars. To train, and so let alone to create a model-based simulation of tens of thousands of kilometers, a photorealistic one, that is a huge task already by itself. But let's say you've created that type of simulation engine to actually run those virtual agents through those environments would take many supercomputers, right? And doing that at scale is a huge challenge. So in Vista, actually, those tens of thousands of kilometers of data in a couple hours, that's all done on a single desktop machine. You can think of a commercial grade NVIDIA GPU that's in that machine. So very commercially accessible. And just to give a sense on some other performance numbers, all of the sensor simulation runs roughly at real time currently. That's without a lot of engineering tweaks as well. So roughly, if you want to run a camera simulator in Vista, that's going to run at the same speed as it would run in reality. And you can parallelize that, obviously, across many different instances, but each instance will be, in real time and independent.
And just the second one on commercialization. So there were a few questions like from Samuel on, do you envision this open source system beating something like Tesla has? Because Tesla sort of has like the maximum VMTs, that they gather from their cameras and that they process. And so Eric had mentioned that he feels that simulation is the only way to meet validation mileage requirements for testing and to try and get as many edge cases as possible and to filling that gap. So I mean, we know that Tesla has a huge lead in this, but you said you're working on a platform to open that you can accept other data as well. So say if a company like comma.ai, which has these cameras, which they get like tons, millions of miles of data, they start inputting this into your system. Do you envision a system which can actually be on par or even better than, a behemoth like Tesla?
Well, let me start by saying that not all data is equal. In fact, most of the data collected directly from cars is pretty boring, right? Like how many times do you have a near accident? Going in lane, following a lane has been really the core of all autonomy solutions, and it's a very well understood problem. The challenge is to get to the corner cases and to get to the situations where you have to do something different than follow. So Tesla is very good at following, and we don't know how what they have in-house for other kinds of situations. But our solution is aimed at accelerating the ability to get at good data, because not all data is equal. There is the data that brings you new information, that brings new knowledge into the system, and then there's the data that is more of the same that you already have. With our situation, with our system, you can get to that new data much faster. And as far as whether we are going to commercialize this, for now, we want to advance the knowledge, which is why we open sourced this tool, because we think it's very valuable, and we think academics and anybody who wants to create the next knowledge frontier can use it. I want to emphasize the system is not for commercial purposes, and perhaps at some point we will consider a commercial application, but for now we want to encourage advancement, and we want to see the capabilities and the knowledge accelerate.
Thank you. So you all would have been aware of the current IEEE 2846 standards. They've defined like 8 scenarios, various scenarios: car following a car, pedestrian walking onto the street. So are you all following some sort of a pattern where these vehicles in these scenarios will behave in a certain way, or is it more of just inputting the data, let the system learn on its own, and then deploy it to the best possible manner on the street?
No, it's actually very mixed, a hybrid approach actually between these two. So of course we want to not only rely on the simulations that have been handcrafted by us as humans. We want to actually explore the full range of this environment to see what's possible. Maybe there are edge cases and situations that it's hard for us to dream up, right? But in simulation, through random chance and enough mileage, you may observe these, right? And it becomes a very sustainable and scalable approach to realizing that dream. Now, on the other hand, I think there is a huge advantage towards having a simulation platform that can have these tunable knobs that you can control and modify to your heart's desire, and you can actually craft the types of scenarios and environments that you care about the most. And I think that's especially important for evaluation purposes, not only for training, but especially in the case of evaluation, where you want to make sure that whatever you're deploying into reality meets some standard baselines or behaves in the ways that you would expect to be congruent with the rules and regulations of the streets. And I think what we've created in Vista has been very much tuned to both of those visions. We've wanted to create something that can both explore the vast variety of the data to see these things that we haven't thought of yet, but also gives us that tunable knob so that we could do that if we wanted to.
Thank you.
Great. Yeah, so we're running against time now. Alex and Daniela, this is really brilliant. Thank you so much for joining us today. So everybody, please join me. I thank Alex and Daniela for the presentation and the conversation.
Thank you for being here and for staying with us all the way till the end of the hour. We'd love to come back to continue the conversation sometime.
Definitely.
Yes.
Then Alex, do you mind joining a break room for like 1 minute? I have 2 quick questions for you. And also to announce that next week, unfortunately, Professor Hani Mamasani had to postpone the talk to spring 2023. So we'll not have a talk next Friday.